Hello everyone. In this presentation, we will understand how the electromagnetic waves behave when they encounter the dielectric and conductive medium. We will explore the key aspects such as the refractive index, the relative permittivity, and the interference variation that occur with the changes in these properties. Let's see the propagation of electromagnetic wave in dielectric medium. When an electromagnetic wave travels through medium, you can see some changes in their behavior, influenced by the properties of that particular medium. In linear dielectrics, in this slide, we can see that electric polarization is directly proportional to the electric field, whereas the magnetic magnetization is directly proportional to the magnetic field. These two relationships decide how the wave will interact with the medium. Also, when the vibrational frequencies of the molecule within the material comes into play, a large number of energy may be absorbed from the electromagnetic wave to cause and maintain this vibration. Here you can pause the video and see the changes in Maxwell equation for perfect dielectric medium. Let's see the refractive index for electromagnetic waves in dielectric medium. The refractive index is defined as the ratio of the speed of light in vacuum to the speed of light in that medium. The refractive index of the dielectric medium is depend on its property, like the density of the material and the molecular structure. And you can see the relation between the dielectric constant and the refractive index. The curve is a parabolic type curve. In short, the refractive index of the electromagnetic wave in dielectric medium determines how the speed of the wave and the direction changes during the interaction with different dielectric medium.
Moving on, we will focus on the variation of relative permittivity with temperature, especially highlighting the integrating behavior of water. Here you can see from the equation 4 known as the Debye equation that describes how the relative permittivity of water decreases as the temperature increases. Here is a dataset starting from the minus 60 degrees centigrade to 100 degrees centigrade and the corresponding scatter plot, taking temperature along x-axis and relative permittivity along y-axis. From the curve, you can clearly see that wavelength of EM waves changes depending upon the properties of the material. In the air, the waves move 2.5 meter over one cycle, but in the glass, it only moves 1.25 meter. So it's clear that the wave number changes in material transition. In real dielectric, the phase velocity depends on wave's frequency. This effect is known as dispersion. From the figure A, you can clearly see as the frequency increases experimentally, the refractive index rises to maximum value and then drops to a minimum and then rises again. The drop in refractive index generally happens over a narrow frequency range and is called anomalous dispersion. Here is a table that shows the absorption region spectrum for different material and their corresponding wavelength. Most of the materials that absorb in the visible region appear colored.
Here's the second part of this project, electromagnetic waves through a conducting medium. To understand this, at first let's see the Maxwell's equation in equation 7. From the equation of continuity, we can get the relation for charge density in equation 9. It's an exponential decaying relation. Here tau has the order of 10 to the power minus 19 seconds. So in no time charge will come to the surface and we can take charge density 0 inside conductors. Thus, Maxwell's equation will be modified to equation 10. From this we can obtain equation 11. This equation is similar to the equations of damped oscillations. We can interpret the solution in equation 15, but if we take the equation 12, k will be complex and it's obtained in equation 13 and 14. Here alpha determines the wavelength and velocity of the wave. We can write k in polar form having phase phi and tan phi equals to beta by alpha. Now we have obtained equation 18, which shows the real part of the fields inside conductors, and here magnetic field lags by an angle phi with respect to electric field. Now we will move to the central topic, skin depth. It's the reciprocal of the attenuation constant beta. We have obtained values of skin depth using values of beta here. Here's an analysis of data for skin depth. We have collected values of permeability and conductivity of different metals and calculated skin depth at different frequencies. By using this data, we have plotted graphs between frequency and skin depth. The logarithmic graph, we can see the orders of values of skin depth clearly. The values are in micrometers, so signals can penetrate very short distance to metals. To apply it in real life, signals can be blocked inside a room by using metal pins. The highest value of delta is in centimeters. This phenomenon of flowing alternating current only at the surface of the conductor is known as the skin effect. So that by this project you can get some understanding about the propagation of electromagnetic waves in dielectrics and conductors. Thank you.